Hello, is it me you're looking for? This is Ma'am Vici again. Our discussion on this video focuses on fluid flow phenomena, which is a subtopic of momentum transfer. I will be giving you a brief background on Newton's law of viscosity, Newtonian and non-Newtonian fluids, and Reynolds number. I excluded dimensional analysis in fluids from my discussion, but I will refer you to a separate video which is solely dedicated to discussing this topic. And of course, I included a video to illustrate an exercise problem on Reynolds number in a pipe. In simple terms, Newton's law of viscosity relates the fluid's resistance during parallel laminar flow to the rate of deformation when the fluid is acted by shear forces. The derivation of the equation of viscosity is visualized by considering a fluid moving between two parallel plates where one of its plates is moving while the other is stationary. If a fluid has a large viscosity, the flow will be slower because its molecules create bigger internal frictional forces, bigger resistance. Whereas, if a fluid has a low viscosity, it will flow easily since there is lesser resistance created by its molecules. Please refer to the link for better understanding and visualization. The equation for viscosity is therefore tau equals mu times dV over dy, where tau equals shear stress, dV over dy equals to the rate of shear strain, v is equals to the velocity of the fluid, y equals the distance of the moving plate from the stationary plate, and mu is equals to the viscosity, which is actually a proportionality constant. However, viscosity is dependent on temperature and composition and pressure of the fluid, but it is independent of the rate of shear strain. To determine the viscosity of fluids at different temperatures and 1 atmosphere pressure, you can refer to the table of viscosities and its corresponding graph like the one I will be showing you. From this table, you get the coordinates x and y for the specific substance. For example, for acetaldehyde, x equals 15.2 and y equals 4.8. This is the accompanying graph of the table just shown. We will use the coordinates we obtained from the table on the graph to determine the viscosity. On the intersection of x and y, connect it with the temperature and extend it to the viscosity line to read the value of the viscosity. I advise you to familiarize with these tables and graphs that is found in the Chemical Engineer's Handbook. The units of viscosity can be expressed in CGS system or gram per centimeter second, poids, centipoise, or cp. In the SI system, we have Pascal second or Newton second per square meter or kilogram per meter second. For the conversion of centipoise to other units, please take note of the conversion values shown for 1 cp. It would be to your advantage to memorize the conversion value of 1 cp to the English unit of pound mass per foot second, and at least one value for the conversion of CP to the other CGS and SI units, since I assume that at your current level of knowledge, the conversion within these two systems are or is already a piece of cake. There are two categories of fluids based on the rheological behavior defined by the Newton's law of viscosity. One is Newtonian fluids and the other is non-Newtonian fluids. The plot of the shear stress versus shear rate shows the different types of fluids. Curve A shows the fluids that has linear relationship between shear stress and velocity gradient. These fluids follow Newton's law, hence they are called Newtonian fluids, and our examples are gases and most liquids. Curve B behave as a rigid body and don't flow at all until a minimum shear stress tau O is attained, after which it flows linearly as a viscous fluid at a stress greater than tau O. These materials are called Bingham plastic fluids like paints and toothpastes. Curves C are called pseudoplastic fluids like paper pulp, blood, syrup, and molasses. The curve passes through the origin. It concaves downward at low shears and becomes linear at high shears. With increasing shear stress, the viscosity of the fluid decreases. This is shear rate thinning. Curve D are called dilatant fluids, like sand in water or sand-filled emulsion and cornstarch suspension. The curve passes through the origin, concaves upward at low shears, and becomes linear at high shears. With increasing shear stress, the viscosity of the fluid increases. We call that shear rate thickening. Let us discuss now Reynolds number. Consider tanks A and B that is connected by a pipe. Suppose tank A, as drawn in the figure, is open to the atmosphere. Then the pressure is 1 atmosphere. Tank B, as drawn in the figure, is closed, meaning it has a pressure that is not 1 atmosphere. In this case, the pressure is lower because of the pump. Since there is a pressure difference between the tanks, fluid will flow along the pipe from tank A to tank B at velocity u. The effect of pressure drop on the velocity depends on the type of flow patterns in the pipe and the flow regime. This is where the Reynolds number comes in. Reynolds number represents the ratio of inertial forces to viscous forces. Thus, the equation is nRe equals dV rho over mu, where nRe is equivalent to the Reynolds number, d equals the inside diameter, v is equals to the velocity of the flowing liquid, rho is equals to the density of the flowing liquid, and mu is equivalent to the viscosity of the flowing liquid. The Reynolds number is an example of a dimensionless number. This is generally considered the most important dimensionless parameter in the field of fluid mechanics. Take note, however, that the general form for writing Reynolds number is nRe equals LV rho over mu, where L is the characteristic length. It actually depends on the solid body which is in contact with the fluid. For flow in pipes or tubes, L is the pipe or tube diameter. For flow past flat plate, L is the plate length in the flow direction. Based on the studies of Osborne-Reynolds, there are 3 flow regimes: laminar, transition, and turbulent flow. For internal flow or flow in pipes, the flow is laminar when the critical Reynolds number is lesser than 2100, transition when it's greater than 2100 but lesser than 4000, and it is turbulent when it is greater than 4000. For external flow or flow past flat plate, for nRe lesser than 2 times 10 to the fifth or 20,000, the flow is laminar. For Reynolds number greater than 20,000 but lesser than 3 times 10 to the sixth, the flow is transition. And for Reynolds number greater than 3 times 10 to the sixth, the flow is turbulent. Okay guys, this is not the end of my discussion on fluid flow phenomena. So please click on the link to subscribe. But still, thank you so much.